Greetings everyone. I would like to extend a warm welcome and express my gratitude for your participation in today's webinar titled From Band-Aids to Immunity: Rethinking Virtual Patches for Connected Vehicles. I'm Gregor Knappik, serving as a solution architect for cybersecurity at VicOne, which is a subsidiary fully owned by Trend Micro. I have been on a cybersecurity journey for the past 15 years, beginning with car access solutions. Throughout my career, I have been involved in numerous software development and integration projects, as well as in the secure semiconductor industry, focusing on secure microcontrollers, secure elements, trusted platform modules, and how to pre-provision the keys. One of my biggest interests was how to patch these complex embedded systems that will be out there for many years, and this is also why I'm here, to start a discussion on patching critical and exploitable vulnerability software. You can expect during this webinar that I will present the target systems for this webinar and what hackers think about our embedded software. The cyber attack detect and respond journey will enable us to discuss issues with software patching that may arise and what can go wrong when we patch software. I will share you insights from the IT world and how virtual patching of embedded devices can help our world. Finally, I will walk through selected examples of recent automotive vulnerabilities and show a demo how virtual patch would have blocked the exploitation of the well-known bash shell shock vulnerability. At the end of my presentation, I will finish with conclusion and recommendations. The target systems for this webinar are diverse, and while there will be a particular focus on passenger cars, it is important to note that other vehicles and systems face similar challenges in securing their software and providing patches. Below is a list of some of the target systems we will be discussing, but this list is by no means exhaustive. It is crucial to recognize that each of these systems has unique characteristics that require tailored cybersecurity solutions. Hackers are particularly interested in embedded software within our industry due to the potential for financial gain or to cause harm to individuals or organizations. In fact, a user on Hacker News posted the following quote on June the 10th, 2 years ago. This post highlights the growing concern about the significant number of security vulnerabilities disclosed each year and the challenges faced by businesses with limited resources and operational constraints to deploy patches quickly enough. The goal of this webinar is to share IT best practices and technologies such as deep security virtual patching that can aid in the patch management process by providing protection against exploitable vulnerabilities, ultimately enhancing the security of embedded software within our industry. When it comes to cyber attacks, the process of detecting and recovering from them can be a long and complex one. In the rush to get products out, companies may leave holes that hackers can exploit, especially if they are pushing out software updates on a frequent basis rather than conducting thorough security tests. This can be seen in the example of utility companies that need to open an API to allow the public to see the consumption, but rushes to implement it due to the deadlines or regulations missing necessary security checks. Patch management is crucial in cybersecurity, as it involves regularly applying patches, fixes, updates, and improvements to software to prevent existing vulnerabilities from being exploited by cyber attacks. In the automotive industry, this means that when an attack reaches the in-vehicle ECU, the host IDS system detects an anomaly, and the PCERT team works on the detected anomalies to isolate the issue. However, the process of issuing a fix can take months or even years, as the supplier needs to develop the fix. Purchasing needs to contract, and the OEM and suppliers need to go through the development cycle and validate the mitigation before providing the fix with the next service pack. Here, the availability of pen testers can cause an additional delay. During this time, the vulnerability remains exploitable until a bug fix has been provided. It is important to acknowledge that the time it takes to provide a software patch varies depending on the complexity of the issue and the supply chain involved. Nonetheless, this process can take months or even years, leaving the vulnerability open to exploitation. The challenges of vulnerability management in our industry are significant, as the vehicles in question must be supported for up to 20 years or even more. One of the dilemmas of software patching is that there is no time for security tests if patching is done on a very fast frequency, like a weekly basis, while the vulnerability remains exploitable if the patch takes more time to test and is deployed on a less frequent basis, such as every quarter or half year. This is further complicated by the fact that some vehicles, such as trains that are also driving in remote areas, require devices to operate independently without connectivity. Other challenges that can make patching even longer include cost reduction, official patch deployment delays, and the need to preserve uptime, as patching a vulnerable system can affect the core functionalities. Patching has always been an issue for organizations, as they know the benefits of patching quickly, but may be hesitant to deploy any updates that might hinder their operations or impact critical systems. This can be further complicated by limited resources, overlooked legacy systems, or systems that are so old they cannot be patched. As a result, many businesses accept the risk associated with not patching, even though urgent countermeasures are needed to prevent attacks, which can cause significant operational downtime and overhead. Compliance issues such as GDPR fines or the PCIs, the payment card industry, stringent patching requirement must also be considered. Recently, a number of vulnerabilities have been discovered affecting the key fob systems in the newly designed models of an OEM's vehicles. These vulnerabilities date back to 2012 and include a replay vulnerability affecting the remote keyless system in vehicles made between 2016 and 2020. This vulnerability allowed researchers to eavesdrop on unencrypted radio frequency signals and recreate them, giving them the ability to open and start vehicles. To mitigate this vulnerability, the OEM and other car manufacturers developed a rolling code system in keyless entry systems that uses a pseudo-random number generator, and to create several different codes between the key fob and the car. However, security researchers from StarV Lab found a way to exploit this rolling code system by capturing the different codes generated by the pseudo-random number generator and using them to eventually open the vehicle. They tested the most popular models of the OEM released since 2012 and found all were susceptible to the attack. Other researchers have confirmed that the attack works, highlighting the seriousness of the vulnerability. The OEM has stated that all completely redesigned recent years models have an improved system that address the issue. However, the fact that the vulnerability has been present for almost a decade and affects a wide range of models underscores the importance of continuous cybersecurity monitoring and prompt patching to ensure the safety and security of connected vehicles. WannaCry. The WannaCry cyber attack was a reminder for us of the potential damage that can be caused by a global cyber attack. If industrial controllers have been targeted, the fallout would have been even more devastating. Operation technologies like PLCs are even more vulnerable to cyber attacks and lack basic security controls, making them difficult to patch and protect as well. This is especially challenging in environments where continuous processes cannot be stopped for patching and where concerns around operational safety and stability can hinder patching efforts. To protect against cyber attacks in operational technology environments, a defense-in-depth approach is needed, which includes multiple layers of security starting with perimeter defenses and network defenses, right down to protecting each and every critical asset. However, for decades, organizations have not deployed these defense layers beyond the perimeter, making it easier for threats to find their way into these networks and compromise critical assets. Despite the availability of patches that could prevent infections, many companies and users still have vulnerable systems. Systems were difficult to patch for several reasons. First, the control logic that these systems execute is critical to the safety and proper functioning of industrial processes. If a patch introduced a bug or error, it can cause the system to malfunction or even shut down, leading to significant downtime and potential safety risks. Second, many industrial processes operate continuously and cannot be stopped for patching. For example, turbines cannot be taken offline for patching without causing significant disruption to operations. This makes it difficult to apply patches in a timely manner, leaving these systems vulnerable to cyber attacks. And lastly, there are concerns around operational safety and stability that can hinder patching efforts. Companies may be hesitant to apply patches that could potentially impact the safety or stability of their operations. This means that even when patches are available, organizations may delay or avoid applying them, leaving their systems vulnerable to cyber attacks. Overall, incident response teams in the IT world follow a structured and methodical process to quickly detect, contain, and mitigate the impact of cyber attacks. This helps to minimize the damage caused by an incident and restore normal operations as quickly as possible. When it comes to incident response in the IT world, there are several steps that response teams typically follow to mitigate the impact of a cyber attack. Enterprises face a range of risks, including compromised networks, systems, endpoints, and security policies, as well as the exposure of sensitive personal and mission-critical data, and the potential for reputation damage and financial losses. To mitigate these risks, organizations need to have the right tools in place. And one technology that can help complement existing patch management processes is virtual patching. Virtual patching provides an emergency security tool that enterprises can use to quickly address vulnerabilities on an affected servers and endpoints. By shielding vulnerabilities, virtual patching can help prevent attacks and minimize the impact of any security incidents. According to a previous survey, some companies took over 100 days in IT world to patch vulnerabilities, but there has been a positive shift in recent years. A Forbes and BMC survey found that companies are now committed to improving their patching practices. The survey showed that a majority of executives identified investments in IT and patch automation systems as delivering the best returns on their security investments in the past year. Additionally, around 43% of the surveyed companies indicated that they would prioritize timely patching and remediation moving forward. Virtual patching and using audit tools are effective solutions for interim protection and scheduled patch cycles. Attackers are now using known and near zero-day vulnerabilities, making it necessary for organizations to also focus on threat intelligence capabilities. Technologies such as Virtual patching and application control can help organizations avoid the burden of ad hoc patching. A comprehensive security strategy should be multi-layered, leveraging various technologies, including virtual patching and application control, in addition to a network defense. Virtual patching, also known as vulnerability shielding, is a safety measure against threats that exploit vulnerabilities. It is implemented through layers of security policies and rules that prevent and intercept an exploit from taking network paths to and from a vulnerability. Virtual patching serves as an emergency security tool that organizations can use to instantly address vulnerabilities on affected endpoints and servers. Unlike traditional patching, it fixes flaws without touching its libraries, the OS, or even the device it is running on, and focuses on changing or eliminating dangerous behavior. Deep security virtual patching gives the option to protect apps without patching them, is faster, doesn't require application language programming, and controls the patch cycle without compromising security. All of this can be done without keeping production servers down, allowing businesses to stay up and running. So virtual patching is a security tool that can quickly address vulnerabilities on servers and endpoints, providing additional time and flexibility to assess and apply necessary patches. It also avoids unnecessary downtime, as we learned, improves regulatory compliance. Additionally, it provides an additional layer of security to components in the IT infrastructure, for which patches are no longer issued or are too costly to patch. And virtual patching offers a more efficient and effective way to secure systems and networks against vulnerabilities. Taking a moment to reflect. How can virtual patching act as a temporary solution and help us in our situation? It could serve as a valuable tool to alleviate stress and anxiety within a company when a critical vulnerability is discovered. What do you think about this idea? In our industry, the response to a potential cyber attack would involve implementing a host IDPs in the ECU to detect and block attacks in real time. However, if a new type of attack manages to bypass these defenses and reaches the in-car ECU, the PSIR team now has access to a more powerful toolset. Instead of waiting for a physical software patch, they can respond immediately with a virtual patch that is quicker and more readily available. To create virtual patches and export rules, organizations require threat intelligence from various sources such as Trend Micro, VicOne, the Zero Day Initiative, SRG, AutoISAC, among others. Vulnerability data comes from the software bill of material, which is updated periodically by the vulnerability management tool that scans the software binary images. The process of creating rules and testing includes threat and vulnerability analysis, rule creation, hit rate and false positive testing, and performance and compatibility testing to ensure minimum false positive rates and no impact on the target environment. Once the rule is qualified, it is optimized and a virtual patch file for the target ECU is created and stored in a database. Different vehicles might require different patches for various ECUs, and verification is done before the deployment to the vehicle. What might an end-to-end solution look like, for example, for an AUTOSAR-based ECU? So in this scenario, both the gateway and the telematics unit have a host IDPS system that utilizes the AUTOSAR framework in this case. So some of you maybe know from the new AUTOSAR release, the IDSM, the manager, IDSR, the repeater, that forwards basically the data further. The system inspector monitors activity, including processes and network activity, and executes reaction commands as needed. The IDPS engines provide detection logs to the AUTOSAR IDSM, which aggregates and forwards the logs between the two ECUs via Ethernet or CAN. Then the telematics unit receives the logs from the gateway ECU, and the TCU has its own IDPS system that can detect and forward events to the AUTOSAR IDSR module. Ultimately, the data is then sent to the vehicle SOC backend for analysis. Now, the OEM has the option to respond by updating firewall rules, access control policies, CAN anomaly detection models, configurations, or virtual patch patterns. These updates can be distributed also to other ECUs to trigger on-device reactions, such as blocking a connection to an identified command and control server. Next, I will show you examples of vulnerabilities and how the exploitation of the system could have been prevented with virtual patching. Probably everyone heard about Log4j. Let's begin with the Log4j vulnerability, which has been widely publicized. Sebastian Dudek, a researcher, wrote a comprehensive analysis report, and the link is also provided in the reference section at the end of the slides. It is a critical vulnerability that allows remote attackers to execute arbitrary code and take control of affected systems via the Apache Log4j library. I won't delve into the specifics of the vulnerability, but it's worth noting that some EVI modules in vehicles that run on an outdated Android system are still vulnerable, as seen in the figure on the right. This system can be compromised by sending a malicious packet via the Log4j vulnerability. Using this well-known example, a virtual patch would involve updating the intrusion detection protection system pattern rule, the IP table, firewall settings, deploying to the EVI, and enabling the protection mode. In this way, virtual patching can prevent malicious traffic related to the Log4j vulnerability pattern before the OEM provides new firmware. Keen Security Lab discovered security vulnerabilities in Bluetooth and vehicular diagnosis functions on a car, which could compromise the AVN unit, internal CAN network, and related ECUs. Through these vulnerabilities, attackers could wirelessly take control of the AVN unit and inject malicious CAN messages into the CAN network to cause unexpected physical actions. In a possible wireless attack scenario, the in-car Bluetooth service is compromised through vulnerabilities, and the attacker deploys malicious codes that allow them to connect to a Wi-Fi hotspot and remotely spawn an interactive root shell of the DCU system. From there, the attacker could transmit arbitrary CAN messages through the Wi-Fi network, trick ECUs into executing diagnostic functions, and trigger unexpected physical motions in the car. So these were in a nutshell the tactics and techniques required to exploit this vulnerability. Implementing a virtual patch that contains a new whitelist pattern and behavior monitor log to prevent remote code execution of the Bluetooth service as a response to the attack in step 1. Identify any privilege escalation attempts from the Bluetooth service which may send malicious packages to the in-vehicle network interface in response to the attack in step 2. During Pwn2Own Vancouver 2022, the Synactive team used an exploit chain to gain remote code execution on a Tesla Model 3 infotainment system via Wi-Fi, without any user interaction. The attack scenario involved setting up a fake Tesla service Wi-Fi access point near the vehicle, and once the Tesla Model 3 connected to the access point, the attacker exploited 2 vulnerabilities to crash and restart Coleman and inject shellcode. The shellcode bypassed the protection and sent a crafted package to the gateway. And finally, the internal service was triggered via the gateway, resulting in opening of doors and windows. The impact was loss of control. The attack scenario involves wirelessly taking control of AVN unit and injecting malicious CAN messages to the CAN network to cause unexpected physical actions. To prevent the attack, we could deploy a virtual patch that includes IDPS pattern to block the malicious packet with an anomaly header, with the figure 4 on top, and additionally deploying a new whitelist setting that will prevent the network configuration from being changed from other service attacks, as in figure 4 bottom. It's important to regularly review and update virtual patches and whitelist settings to address new vulnerabilities and emerging threats. Now I will be demonstrating how virtual patching can be used to mitigate the bash shell shock vulnerability. For those who are not familiar, the bash shell shock vulnerability is a vulnerability that was discovered in 2014 in the widely used Unix bash shell. The vulnerability allows attackers to execute arbitrary commands on a vulnerable system by manipulating environment variables used by the bash shell. In short, this allows for remote code execution on the target systems. So let's jump into the demo. First, we have a virtual machine running a vulnerable version of bash. We'll try to exploit the vulnerability by running a simple command, and the telnet command is used for interactive communication with another host using the telnet protocol, targeting the IP, the target's victim IP. I run this script on the attacker machine and connect to the victim machine. As you can see, the request includes this string here, which is the exploit code. When the target system receives this request, it interprets the code as a command and executes it. The key feature of the Linux telnet client is -L user. When looking into the manual pages, it gives us the information that it specifies user as the user to log in as on the remote system. Means the -L option specifies the username, telnet, host IP address, -L user. The username in this case is a malicious code injection that takes advantage of the shell shock vulnerability to make the victim execute the specified command, bin eject. The eject command is a harmless command that is used to demonstrate the exploit. In a real attack, This command would be like something /path/ something evil. So let's switch to my second screen here, where I have prepared two virtual machines. One is the attacker, the other one is the victim. And I have recorded a demo where I will demonstrate how to exploit a bash shell shock vulnerability. The demo is divided into 3 parts. Firstly, I will execute the attack on a fully unprotected victim ECU. You will always be able to recognize the victim and the attacker here. That is running automotive grade Linux system. Next, I will activate a host intrusion detection system with a rule set that does not consider the shell shock vulnerability. Finally, I will deploy a virtual patch containing an additional rule set that will allow the host intrusion detection and protection system to prevent the attack. The left side of the screen shows the terminal window of the attacker, and on the right hand side you can see the victim automotive grade Linux system. In the first part, I will check the IP address of the victim machine to ensure that I am connecting to the correct system. Okay, as you can see, yes, it is 10.0.2.5. Then I will double check that the DPS system is deactivated. So let's clear the screen and show that also the intrusion detection system is stopped. So you can see there's various DPIs, for example, the packet inspection. VM means monitoring system, behavior monitoring system. So the intrusion detection prevention system is stopped at this stage. Okay. So let's type in here. We'll use first to the terminal window of the attacker, executing the telnet command to connect with the IP address of the victim machine. We are using the non-dangerous command eject. The connection is successful, and I can log into the victim machine. Let's break at this stage and move on. Okay. In the second part, I will activate the host IDPS on the victim machine. So we see the system started in online mode. So as you can see now, the same command as before has not prevented the attack. So we received the connection to this victim IP, and we are able to log in to the victim system. Okay, let's move on. Let's break it from here. Stop the further execution. In the third part, I will apply now the virtual patch with a new rule set on the victim machine. The rule set is designed to protect the system from the exploit. So I'm executing the command to update the system. It's a demo system, but still we have done some very basic authentication. Need to enter password to apply the new pattern. You see pattern applied successfully. And now let's go to the attacker screen. Let's make first the update. So we see basically that the pattern is installed. And let's move on to the attacker screen. And now, as you can see, the connection has been closed by the victim's host. And even though the vulnerability still exists, the new rule set provided by the virtual patch helped the system to protect itself. Now we are at the end of our time today. I hope you feel more comfortable and confident about virtual patching and managing your vulnerabilities. We learned today that patching is absolutely necessary because our industry is one of the longest lasting exploitable targets, and regardless of an organization's size, while it might take time and resources, it becomes less of a strain on operations once proper procedures are established and effective solutions are in place. As several companies have noted, it is well worth the investment also in bug bounty program like CTI to improve the cybersecurity posture. Of course, virtual patching is a valuable technique to respond to an event immediately. However, it is not an alternative technique to permanent patching. Virtual patching can only ensure reliable protection in the interim. You still need to deploy permanent patching whenever possible, and a failure to apply patches promptly can have serious security consequences. And we learned today to mitigate non-public vulnerabilities. Once, we need other weapons like threat export rules, whitelists, access control, a VSOC, and a P13. I promised to provide a list of valuable references that I have used to prepare my presentation. So here you find the list with the references and in brackets also the position for the specific topic. And also a list of resources that I can recommend you about vulnerabilities and virtual patching if you like to read more about them. I would like to provide some information about the company I am working at. VicOne is an independent company that originated from Trend Micro's automotive cybersecurity research and expertise. As the demand for automotive security solutions increased, VicOne was launched to cater to growing need. Currently, we have 4 main offices located around the world, and our focus is to secure organizations globally by providing automotive cybersecurity software for various VSOC initiatives, host intrusion detection protection system, a vulnerability management tool. Additionally, we conduct research on automotive threats and offer professional cybersecurity threat intelligence services for the automotive industry. I would like to take a moment to express my gratitude to ASRG for making this webinar possible. If you would like to stay connected with me, feel free to connect on LinkedIn or send me a message. Thank you for your attention today and have a great rest of the week. Stay safe and goodbye.